Hello and welcome. My name is Alessandro Ciaccia and today I'm presenting my MSc Computer Science dissertation, Breaking the Clone Army, Emergent Stability in Peer-to-Peer Microgrids via Behavioral Heterogeneity. To begin, the global shift toward localized renewable energy, such as rooftop solar panels and residential batteries, has fundamentally altered our electrical grids. Historically, electricity generation was centralized and unidirectional. Today, prosumers actively manage local generation and storage. While this transition is environmentally beneficial, it has introduced severe operational challenges for distribution system operators. The most prominent of these challenges is the duck curve. Midday solar generation peaks when demand is low, causing net utility loads to drop to near zero or negative levels. In the evening, solar output falls off just as residential demand surges, requiring massive, expensive evening ramping. California isotelemetry shows evening ramps routinely exceeding 17,000 MW within a narrow 3-hour window. This forces operators to curtail clean solar energy during the day and activate high-emission gas peaker plants in the evening. Peer-to-peer energy trading markets have been proposed to balance this by encouraging midday consumption and staggering evening discharges. However, a critical vulnerability exists in the current literature: the assumption that prosumer agents are perfectly rational, identical, profit-maximizing actors. When you deploy a population of homogeneous, profit-driven agents, they inevitably learn the exact same optimal policy, converging to a state of pure Nash equilibrium. In a microgrid, this manifests as the clone army effect. Every AI agent coordinates to dump their batteries into the local market at the exact same peak tariff hour. In our research, we mathematically modeled this as a continuous space iteration of the prisoner's dilemma. Because localized price clearing is a function of aggregate supply, if both players export simultaneously, they crash the clearing price. The action to export strictly dominates for both players, leading the system to a Pareto suboptimal Nash equilibrium, where coordinated, staggered behavior would yield a far higher community utility. To analyze this market collapse further, we formalize the P2P market under oligopolistic competition. Under core-node quantity competition, prosumers simultaneously decide on their export quantities, which clearing prices react to. Under Bertrand competition, agents compete on price, undercutting each other to ensure their battery discharges during the high tariff window. In both models, a homogeneous population of profit-maximizing reinforced learning agents is bound to converge to a destructive, symmetric Nash equilibrium that mimics a local market collapse. To resolve this convergence, we inject behavioral heterogeneity. Translating these behavioral archetypes into the neural networks of multi-agent reinforced learning agents requires integrating prospect theory. Instead of maximizing linear wealth, the agents evaluate outcomes relative to a reference point, specifically a critical battery safety buffer. We implement a nonlinear value function, v of x, with a loss aversion coefficient lambda approximately 2.5. This penalizes risk-averse agents severely if their battery drops below their safety buffer, modeling psychological range anxiety. Moving into Chapter 3, the methodology and system architecture, we first establish the physical microgrid foundation. To bridge standard multi-agent reinforced learning with physical reality, we implement nonlinear physics models. Battery state of health degradation using a rainflow counting algorithm, and temperature-dependent PV efficiency losses during ambient heat waves. Next, we wrap these physical dynamics into a custom Gymnasium Python class. The code snippet in section 3.2.3 demonstrates the architecture, handling our 6-variable observation space, representing battery state, grid price, solar irradiance, background earth load, risk aversion, and green factor, and stepping the simulation in a standard reinforced learning libraries expect. Finally, we map our prospect theory logic directly into the PPO agent's composite reward function. The formulation combines monetary cash flow with a quadratic resilience penalty and a green penalty. By adjusting these weights, we segment the population into 3 tribes based on Rogers' diffusion of innovations: the profit-seeking greedy tribe, the conservative eco-warriors, and the balanced majority. Let's examine our results. Under the baseline homogeneous control scenario, all agents synchronize their battery discharges, creating a severe midday load peak of 2.82 kW and a power of 2.67. However, under the heterogeneous universal brain model, behavioral divergence staggered discharge times across 6 to 8 p.m., reducing peak load by 12.8% down to 2.46 kW. By breaking the synchronized clone army behavior without a centralized controller, behavioral heterogeneity successfully achieves emergent self-organization. Furthermore, sensitivity analysis proved that if default profit maximizing algorithms are deployed to more than 45% of smart homes, such as in the scenario C, Tech Bro Grid, the grid collapses back into the clone army state, proving that behavioral diversity is a physical grid asset. During extreme winter storms, such as in our scenario F stress test, solar generation falls to zero, causing a total local market liquidity collapse and forcing all agents to revert to pure utility imports. Scrolling into chapter 5, we directly answer our research questions. For research question 1, our results prove that autonomous agents achieve emergent stability without centralized control. For research question 2, behavioral heterogeneity breaks Nash convergence by dispersing execution times into a mixed strategy equilibrium. This establishes what I define in section 5.2 as the prosumer trade-off. While risk-averse hoarding stabilizes the physical grid by capping peaks demand by 12.8%, it also restricts local peer-to-peer trading liquidity by 78.1%, preserving at the same time overall community self-sufficiency at 64.8%. For future research, in chapter 6, I have outlined 3 key computational integrations to move this into real-world grid deployments. First, federated multi-agent reinforced learning, which aggregates neural gradients locally using federated averaging to preserve absolute household data privacy. Second, Stackelberg-Gam theory integration to model hierarchical leader-follower relationships between microgrid utility operators and prosumers. And third, topology-aware graph neural networks, which represent the grid as a physical graph to calculate spatial voltage constraints. Beyond smart grids, the universal brain framework has broader generalizability. By using behavioral parameters to break symmetric Nash convergence, the decentralized architecture can be applied to solve spatial synchronization in municipal traffic congestion, or flash crashes in decentralized finance liquidity pools. Finally, by recognizing behavioral diversity as a stabilizing feature rather than a system flaw, we can design decentralized systems that are both computationally resilient and aligned with human behavior. Thank you for your time, and I welcome your feedback.